Good afternoon, 61C. Good afternoon. Right. Yeah, sorry I couldn't be here on Tuesday. My house got burglarized, so I was taking care of that on Tuesday. No major damage, but lost a lot of cameras. So, okay. Today we're going to talk about pipelining. So far, just to review, we've been looking at single-cycle CPUs where the entire execution of an instruction starts and finishes within one clock cycle. So you go all the way through from taking the PC, fetching it through the instruction cache, decoding it, fetching register operands, doing ALU operations, accessing memory, and writing back, all within one single large clock cycle. We went through all the steps to build that, analyzing the requirements of the instruction set, what are the components you need, how do you connect them, how do you mux between the different alternatives for different instructions, building the control logic. So all that we've covered. And what we ended up with was this single-cycle data path where, as I just said, everything, there's one clock signal here, starts at the program counter, goes to instruction memory, fetches the bits, you decode them, you fetch the operands, you go through ALU, you maybe generate an address for memory to return some value that you write back, and finally at the next clock cycle you update the register file. Now, if you look at what sets the timing of this, how fast can this processor run, it's basically the sum of all the delays along the longest possible path of any instruction. So of all the thing is you have a fixed clock cycle that you use for every instruction. It just repeats at a constant rate. And so for every instruction, you need to wait the worst case time of any instruction, right? So if you look at the breakdown of for each instruction type, what are the components of completing that instruction, you kind of add them all up. And that's what's happening in this table. So let's assume, for example, these are just some numbers that, let's assume is 100 picoseconds to read a register file or write the register file, but 200 picoseconds for everything else. So let's say instruction fetch, which all the instructions do, takes 200 picoseconds. Reading the registers, which they all do, takes about 100 picoseconds. ALU op, 200. Memory access, which only loads and stores do, take 200. And register write back, which only the load and the ALU register format instructions take. So if you just add up for each instruction the worst case path through all the logic in one clock cycle, you get these total times. And what you see here is the time for each one of these. And the clock period is set by the worst case one. So the clock period is the time of the longest path through all the logic, okay? And the clock rate, just to go over this, we went through this the other day, the clock rate is in cycles per second or hertz, and that's given by 1 over the period, how many seconds per cycle, right? So cycles per second, the reverse of that is seconds per cycle. So by looking at the circuit delays, you can get the seconds per cycle, then you just invert that to get the clock rate. So this lecture we're going to talk about pipelining, which is a way of increasing the clock rate quite dramatically over this worst case to improve performance. So the faster we can execute instructions, the quicker our programs will run on the hardware. So in this case, we see that the load instruction is kind of the worst case instruction. It does stuff in every piece of the process, from fetch and decode and register read and memory access and write back. It touches every stage, so it has the longest total delay. So that means that this processor that executes all these instructions, we'd run it with an 800 picosecond clock period, which would correspond to a 1.25 gigahertz clock rate. If you just invert 1 over 800 picoseconds, gives you 1.25 gigahertz. That would be the clock rate of this simple processor. Now, the key to realizing how to make things go faster, and this is one of the great ideas in architecture, is pipelining. And that is that when you break a task down into stages, sometimes you can overlap the stages of different tasks. So the example we're going to use to illustrate this is laundry. So you guys all know about laundry, right? Some of you occasionally do laundry, right? Or just take a big bag home to your folks. They'll do your laundry for you at the end of every semester. Anyway, so back in the day, we had the naked man at Berkeley. He never had to do laundry, right? So it's another approach that's unfortunately not allowed anymore. So say you had 4 bags of clothing to do. So Anne, Brian, Kathy, Dave, they all have a bunch of clothes to do. So there's 4 bags of laundry to do. And you go through the process. In the washer, it takes 30 minutes. Let's say the dryer takes 30 minutes. Comes out of the dryer, and you guys all fold all of your laundry, right? So that takes another 30 minutes or so, and then you fold it away and put it away neatly in the drawers, right? You all do that, yeah? So it takes another 30 minutes to stash it away. So if you do your laundry sequentially, every stage one after the other, and just map this out. So if I got these 4 batches to do, I first do all the stages for one batch: wash, dry, fold, stash. Then I move to the next batch, batch B, wash, dry, fold, stash, and so on. So it's going to take me, basically 8 hours to do these 4 loads, right? Each component takes half an hour. So by doing 4 loads with 4 stages, it's going to take me 8 hours total to do those 4 loads of laundry. Now, obviously, if you've ever been to a laundrette with more than one batch of laundry, you figure out, I can do this much faster than this. I can pipeline my laundry. Or if in your apartment where you live, there's only one of each. You figure, well, while one person is doing the wash and then moves their stuff into the dryer, the wash is now free. I can put the next load into the washer, right? So while one load of laundry is in the dryer, the next load of laundry is already in the washer. So you overlap all these stages. So similarly, as you go through, while one person is folding the laundry, another batch can be drying, while the next batch is starting off in the washer again. And so you overlap these 4 loads of laundry. And so now it only takes you 3.5 hours to do 4 loads of laundry, right? Instead of doing all of one before you start all of the next. What you're taking advantage of is the fact you have these different resources, that the washer and the dryer, that you can have 2 different loads using those 2 different machines at the same time, right? That's parallelism. This is a form of parallelism. It's one of the most important ideas in computer architecture. Now, some things about this approach, it doesn't help you do any one piece of laundry faster, right? If you got some, cute dress you really want to wear that evening, and you got to wait for it to go through laundry, pipelining is not going to help you get your dress washed sooner, right? You have to wait for it to go through these stages, right? So pipelining doesn't help the latency of a single task. So any given load takes just as long as it did before. So latency, the time to finish one thing, hasn't changed. All that you've improved is the throughput, which is how many loads of laundry can you do in a day, per unit time. And so another important thing is, what's the maximum speed up you can get by doing this pipelining? What's the biggest improvement over sequential you can get? The answer is, it's the number of different stages. So if I have 4 different stages in the process, at best I can overlap 4 things at the same time. So my maximum speed up is a factor of 4 over the base case of just doing all the pieces sequentially. So here I have 4 stages of wash, dry, fold, stash. And so the maximum speed up I can have is a factor of 4, assuming I only have one each of a washer, dryer, a folder, and a stasher, right? So the maximum speed up is given by the number of pipeline stages. Another thing to realize, I don't get a factor of 4 speed up because it takes some time to fill the pipeline, right? I can't instantly put one load in the washer, one load in the dryer, start folding and stashing. I have to sort of ramp up by doing the wash for every one. So they all have to move to that first stage, one after the other. So it takes a little while for the pipeline to fill up. So only at this point am I actually using all 4 things at once. And then after that, I drain down, and here I'm also not using these resources, and I'm not using these resources. Now, when we run programs, and we have many instructions to execute, it's like going to a laundromat. There's many loads of laundry, people bringing laundry from all over, so the machines are constantly busy, and so you are getting that throughput increase. You only see this effect, pipeline fill and drain, kind of at the edges of starting up and finishing off a whole bunch of work. But the peak speed up is a factor of 4, right? But in this case, we only get a factor of 2.3 in this example. Another thing with pipelining that's kind of awkward is it doesn't really help just to speed up one part of the process. Okay, so say, I get a new washer that takes only 20 minutes, and I get somebody who's much better at stashing clothes, and they only take 20 minutes. How much faster does the pipeline get? Runs at the same speed, right? Because I'm still waiting on the dryer, and I'm still waiting on the folder. So because I can't get through those stages any quicker, and you're limited by the slowest stage, I've divided the work into 4 pieces, but I can't move from one piece to the next until the next guy's ready, the next stage is ready. And so the speed up is limited by the slowest piece of the process, right? So in pipelining, you divide all the work up into stages. The slowest stage sets the maximum rate at which things can move through the pipeline. So if a stage takes 30 minutes, I cannot move between the stages faster than once every 30 minutes, right? So even if I'm done in 20 minutes, I'm still waiting 10 minutes for the next stage to be ready, okay? So basically, if you don't divide your work up evenly, and you have what's called an unbalanced pipeline, where different stages take different amounts of time, you're going to be limited by that slowest stage in the pipeline. So one of the goals of pipelining is to divide things up so the stages are roughly equal in duration. Now, this is a very old idea. I mean, this goes back to the start of Industrial Revolution, Henry Ford building cars, where they had a massive assembly line, and his big innovation was figuring out how to break up the work of building one car into these little pieces and having each worker do a little bit and move on. And so this way, he had this massive pipeline execution that made car production much cheaper. Prior to that, people actually built cars one at a time. They'd have one place on the floor, they'd start building a car, they'd put the pieces together until the whole car was done. Right? And that was really inefficient compared to the pipeline assembly process. Let's stop now and apply that to executing instructions. So in MIPS, we already called out these 5 stages of executing the instruction. You have instruction fetch, instruction decode, instruction execute, memory access, and write back. Now remember, not every instruction uses all of these stages. In fact, only the load instructions actually do all of these. But what we did is we set out that every instruction would pass through all those stages nonetheless. So what we're going to do now is take our single cycle data path and pipeline it. So this is the sort of schematic of that single cycle data path. You have the program counter, you feed that into instruction memory. Sometime later, the instruction bits come out. You decode them, send them to the register file to get the operands. Then sometime later, the operands come out. You then execute the LU operation. Sometime later, the output of the LU is ready. That might be an address you're sending to memory. Sometime later, the memory responds. Then you're ready to write back. And finally, you update the register file. So all that happens in one cycle in the single cycle data path. And what we're going to do to pipeline this is just add extra registers in between those stages. So just like breaking up the laundry and doing things in parallel, what we're going to do now is, instead of going all the way from beginning to end for one instruction and then moving on to the next instruction, we're going to just do the instruction fetch for the first instruction, capture the result in this first register. So now you only have to get from here to here in one clock cycle, right? And the next clock cycle, we'll start a second instruction, reading the program counter, fetching instructions, while this guy moves on through decode. So just as with the laundry example, we're not going to wait from start to beginning of each instruction. We're going to overlap them. So when the pipeline is full up, we're going to have, in this case, 5 different instructions at 5 different places in the process of pipeline, right? And this will give us a maximum speed up factor of 5. Now, we need these registers in place because these kind of break the flow of signals between the pipe stages. In a regular circuit that we had before, you launched a new instruction. It would drive the wires at this end coming out of the program counter. Then all this other circuitry, there was just a combinational flow of signals just settling out one after the other, kind of like dominoes falling over till the output settled. And then you would capture it in the results in the register file or the new PC. So you waited for all those signals to propagate all the way through the circuit. In order to separate out the stuff for each instruction between stages, we're going to insert these registers that block the flow of signals just to that register. Then we capture it at that register at the end of the clock cycle, and then launch it into the next stage at the start of the next cycle, right? So this is the way of breaking apart the circuitry into pieces, so different instructions can use different pieces of the circuitry at the same time. Yep, question?
Thinking about branches, how does it know what the next instruction is until the first one's finished?
That's a great question. So if you have branches, how do you know what the next one's going to be? That's a great question. We'll get to that later in the lecture. That's one of the difficulties of pipelining. It's one of the ways that instructions are very different from a car assembly plant. At a car assembly plant, every car is independent. You just go through. It doesn't matter what the previous car was or the next car was. Instructions, though, are meant to be read one after the other. There's a sequential order, and that each one has an effect that the next one has to see. And we'll cover that in the second half of the lecture today. So let's go dive down a level of detail in the pipeline. This is just expanding the figure out a little bit. So what these colors are showing now is we're going to use this for this next set of animations. So this register sits in between instruction fetch and instruction decode, IFID. This register sits between instruction decode and execute. This one between execute and memory. And this one between memory and write back. So for a load or restore, let's say, this is what happens in instruction fetch. We take the PC value, we read the instruction memory. So one thing, the convention in this diagram is when you read from a memory or register file, you color the front of it like this, or the right-hand side. So reading from instruction memory, and we capture it in the this register at the boundary. At the same time, in that same instruction fetch phase, we update the program counter. So notice this add happens here, and we mux in PC plus 4, so that the next clock cycle will have the next, we know where the next instruction to be fetched is, right? So we can do all that in one clock cycle, one of the pipeline clock cycles, so that we can start fetching the next instruction straight away. And we'll come back to what happens in branches a bit later on. This is just a simple case where we're just going straight through the code. So now that first instruction moves to the next clock cycle now, we do the decode for that next instruction. So it's sitting in this register. We do things like sign extend the immediate in here. We also read the 2 register operands. And we capture all those in more registers. So you have these registers just to capture the data we've got. We haven't done any compute on this yet. All we're going to do in this clock cycle is decode and read the register operands and capture them here. Then the third cycle of execution, there's one instruction. Now we get to do the actual ALU operation and capture the result in the this register at the end of that pipe stage. In the fourth cycle, we actually do the memory access. So now this instruction's moved down the pipeline. It's got to the memory access stage. We read the memory and capture the result. Yep, Daniel?
When you say it's a register, do you mean like it stores only 32 bits? Or is it, like, because I see a lot of inputs, like how does it know?
Yeah, so good question. So these registers, when we say register, it's a bit of a generic term. So this is as many bits as you need to capture all those values. So this is a set of flip-flops that are clocked, and they capture all those signals coming in and delay them until the start of the next clock cycle, right? So this cycle, you read the data memory and write it to this register here. And then finally, you take this value and you write it back. So there's one little problem on this diagram, right? We're writing back that load value to the register file. And what's gone wrong here? So if you take a look, normally we wire the register you write to is held in the instruction that you capture during decode. So during instruction fetch, you get the instruction bits. One of the fields in the instruction is the register you should write to. But we did that a few cycles ago, and we moved down the pipeline. And when we get back to write back, there's a different instruction sitting in the decode stage. It's one like 3 or 4 instructions later. And so you don't want to write to the location that it specifies. You want to write to the location you fetched when you fetch the load instruction, right? So you have the wrong register number coming in here. So what you actually want to do is capture the register you're going to write and also register that. So take the instruction bits of the instruction you fetched and move those down the pipeline with the instructions so they stay together. So at each stage, you know the right thing to do for that instruction. Right, so you're taking a copy of the instruction bits and moving it down with the data down the pipeline. So when you get to the end of the pipeline, you know the correct register that you should write to. Okay? Is that clear to people? So when architects draw pipelines, there's a few different ways they draw them. This is a very common way of drawing an instruction pipeline. So you have here the 5 stages: instruction fetch, decode, execute, memory, and write back. And time is going along this way. So one instruction moves down the stages like this. And the vertical bars indicate the different clock cycles. And you can see I'm drawing the second instruction coming down the pipeline, and the third, and the fourth, and the fifth. And you can see by the time we get to here, just as with the laundry, at this point we now have every pipe stage working together in parallel on 5 different instructions. We have 5 instructions in execution at the same point in time. Yep.
On the last slide, how do you keep track of like the instruction or the control bits?
So the question was, how do you keep track of the control bits? Well, you capture them here. So when you fetch them from the instruction memory, they come into this register. Then what's happening here is I'm explicitly capturing those in more bits. There's more register bits needed to carry that instruction down the pipeline along with the data as you process it down the pipeline. So you're keeping track of what was that instruction. And as you go down the pipeline, you use the local version of the instruction register to decode and control things. So you have the right instruction going along with the right data. Just keep them paired all the way down the pipeline. So this needs more registers. You need more circuitry. You need more stuff to hold on to those bits and move them and shift them down the pipeline along with the data. Right, that's what's being shown here, this purple line here.
How does it know to write back to the register? Like you move the instruction down and then
So remember when we talked about decoding the control signals last lecture, there's a table of, if these bits are in the instruction, this means it's a load, and a load, you can decode to mean it writes the register using the address in the RT field. So all that logic, you kind of replicate in each pipe stage. But notice you only need in each pipe stage the control decode for the stuff that happens in that pipe stage. So at the end, you just need to know what register, am I writing a register? And if I'm writing a register, which register is it? So in practice, what happens is as this goes down the pipeline, some of the bits drop off because you've kind of done that piece already. You just need to keep the control bits for the remaining pipe stages, right, as you shift down the pipeline. Question?
So if we were to write into the memory, is it possible to do the second stage and the last stage at the same time?
If you were to write to the memory,
Right first.
right,
So the last part would use the second, like the register there.
yeah, we'll actually talk about that in a minute. So the question's about, it seems to be reading the registers and writing the registers at the same time in the same pipe stage. Yes, we'll talk about that in a second. Good call. So one thing to make this pipelining work is this is one reason why the instructions are designed so they all go down the same set of stages. And in some cases, they won't use anything in a stage, but by making them all look the same, it makes it a lot easier to build this pipeline. So to help draw these figures, they get kind of complicated. We'll use a sort of simplified version of the pipeline like this instead of more detail. So just iCache. So this instruction memory is usually implemented with an instruction cache. We'll talk about caches starting next lecture. But just for now, assume it's a very fast single-cycle memory. And data cache, similarly for data memory, is usually implemented with data cache. But we just use the simplified diagram to show some effects. So let's say we have a string of instructions now going down the pipeline. So we start with a load, instruction fetch. So these are the clock cycle boundaries. So this clock edge, this guy moves from fetch to decode, and the new instruction comes in and does a fetch. Now remember, in this guy's fetch stage, we incremented the PC by 4. So that's the PC that'll be used to fetch the next instruction, the add, right? So that PC is ready in time to fetch that the add instruction in the next cycle. Move to the third cycle. This guy's now in execute. You're now reading registers here. And now this guy is fetching. So this guy incremented the PC another +4 to get to the store instruction. Right, and so on. And so this cycle, 5 cycles later, we have 5 different instructions in 5 different stages of the pipeline. Okay? So that's a big speed up. Now with the register file, we're using this convention. Now notice here, we write back here to the register file. That was this question just now. So the left half we're going to shade to indicate we're writing to it, and the right half we'll shade to indicate we're reading from it. And you notice on this clock cycle, we need to be able to write to it and read 2 values from it within the same clock cycle. So going back to, so what's the benefit of doing this? Well, the question?
If you were trying to write and read to the same register, as in like you load it into register S1 and then try to add with that register, if you haven't rewritten
Right, so the question was, what happens if I'm writing register 3 here, and I'm reading register 3 here? Kind of what happens?
Or even in the next add, like if you're writing to register 3 in the load, and then trying to add using that value.
Right, good catch. So we'll get into that in a few slides, but yes, the problem is, what if this guy is loading into register 3, but this add was wanting to read register 3. I'm writing it here, but I want to read it earlier than I possibly can. So we'll talk about how to handle that. But let's just ignore that. We'll get into the complexities in a minute, but just from the high level, what's the maximum speed up you can get? So the time for a clock cycle, if you pipeline it, the best case is the time of the single cycle divided by the number of stages. If you manage to perfectly divide the work into absolutely even stages, the best case speed up is the number of pipe stages, right? But in practice, you'll never quite get an even balance. And there's some overhead to adding those registers in between the stages of logic, so the speed up will be less than that maximum in real life. So the speed up would be reduced a bit. Sorry. So one of the factors to account for here is the speed up here, to be clear in your head, the speed up is for increased throughput. I'm doing more instructions per unit time. Any one instruction doesn't speed up, just as with laundry, right? Any one instruction, if anything, takes a longer amount of time to complete. But in aggregate, when I look at a whole program, I should be completing more instructions per second, right, per unit time. And that's what gives me a speed up in my program. Okay, so let's take a look at this example. So we went through this before. These are our example numbers for the delays for each portion of our unpipelined CPU. And we figured out that the load was the worst case of 800 picoseconds. Now let's look what happens when we pipeline this. So in the single cycle case, we start here in time and we have to wait 800 picoseconds till the next clock edge. So we'd only clock it here, and then this all happens in one clock cycle. If we pipeline it, now notice we have to balance the pipe stages. So the worst case is 200 picoseconds. We have to split it up into 200 picosecond chunks. But now we can actually clock this once every 200 picoseconds, and data moves down the pipeline. Instructions move down the pipeline. Notice there's some wasted time here, which is because the register read was quicker than the other stages, but we have to use the same clock for all the stages, so we use the worst case of 200 picoseconds. But even so, we've gone from 800 picoseconds, which was the 1.25 gigahertz clock rate, to now this pipeline version. Cycle time is only 200 picoseconds, and there we are, running up 5 gigahertz now, right? It's a factor of 4 speed up from pipelining it over 5 stages, right? It wasn't perfect, but it's a big boost in performance. And so this is one of the big ideas in architecture, and one of the early ideas that really led to massive speed improvements. So, time is some clickers, but I need to. Oh, I got it. Okay, so which statement is false?
So funny.
doubt like there is, but it was too high. It's like beyond the scope of this class. Yeah. It's really cool. Just a lot of flexibility. Yeah, it's just you. I don't know the answer about this relationship. Like I found it actually. It's in these pocket. I would say that for improving your understanding, makes you more flexible for the future. Yeah, for future.
Okay. All right. All right. So a little disagreement. People aren't sure of the answer. So let me give you a little bit of time to chat to your neighbors and see if you guys can agree on what the right answer is.
And that's the most important thing. It's like, because then it's like you can teach yourself. Whereas I feel like this is very different. But it's like, it's not intimidating. It's like my yeah, like section B was too much. It's like I'm doing it. Which means it's like still super important. It's like, but it is, but it's not something that I'm really invested in. You know, if you actually compare like jobs afterwards or having this usually just you know how to really efficiency. Just because you can't understand the part. So if you only understand the software. It's like vertical integration. So, what are the odds of that? Yeah, actually, it just, you would think that, yeah, it's true. That's true.
Okay, so some shift, but there's a clear winner, but there's also some people thinking B is an option. Let's have a look. So which statement is false? Pipelining increases instruction throughput. Yes, that's kind of the whole goal, is to increase the rate at which we can put instructions down the pipeline. Pipelining increases instruction latency. Well, yes, because the pipeline stages aren't perfectly balanced. So as we saw in that last example, you may have to add some dead time in order to make the clock boundaries across the stages line up. And also the registers add some time to get through the register. So if you look at one instruction, the time from start to finish of that instruction will go up. So it will increase instruction latency. So that's true. Pipelining increases clock frequency. Hopefully you are listening. We just said that in the slides a few slides ago. That's the whole goal. So the one thing that is false is pipelining decreases the number of components. You need to add the registers to provide the pipelining, to separate the different stages from each other. So that's the correct answer. Pipelining increases the number of components. Okay, so let's jump into an administrivia question. The question is, when is the instruction latency not increased? Well, so the best case is when you do balance exactly all the pipe stages. But even in that case, the registers that you add delay the signal by some amount. Remember, there's a setup time and a clock to queue time on every register. So they will, even if the pipeline stages are perfectly balanced, the extra time to get through the register will increase the instruction latency. Okay, so administrivia. So we decided to give you a little bit more time for Project 1.2. So now the due date is Saturday midnight, and we pushed homework 4 out to Tuesday at midnight. Now, for those of you who are diligent and were getting things finished on time, what we're going to do is give you 10% extra credit for finishing by the deadline. So extra credit happens after we figure out all the grade boundaries, so it won't affect the rest of you, but the people who did get it early will get a potential boost from the extra credit. Okay? All right. So, one other thing, so the midterm grades, we should have those out tomorrow, I think. Today, tomorrow. Tomorrow, let's say tomorrow. Should be out tomorrow. Okay. So pipelining looks like a great technique. Wow, you suddenly get a 4x speed up. That's a big number. It's very rare you get those kind of speed ups from something this simple. There's got to be a catch or two, and there's actually quite a few catches. So pipelining is plagued by what we call hazards. And so a hazard is a situation that prevents you starting an instruction in the immediately next cycle. And there's 3 major categories of hazard. One that we call a structural hazard. And this is when that, to keep the pipeline flowing, 2 different instructions need to use the same physical resource, the same piece of hardware at the same time, right? If the same piece of hardware is needed across multiple pipe stages, then you might get a conflict that's called a structural hazard. It's because 2 instructions are fighting over the same piece of hardware. That's a structural hazard. We also have a data hazard, and this is when there's actually a data dependency between the instructions. So one instruction needs a value that the previous one is producing, and the previous one hasn't produced it yet, right? So we actually had questions about all these hazards already. And the last one is a control hazard, which is I don't even know what the next instruction is supposed to be because the current instruction is a branch or a jump that's going to change the program counter, not just by +4, but to jump some other random place in the code. So these are the 3 major categories of hazard. And so computer architects have spent a long time trying to figure out how to cope with these various hazards to improve pipeline performance. So the first one is actually the easiest one. So structural hazards are just when you get a conflict to use some resource. So as an example, let's imagine doing this pipeline, but with only a single memory unit instead of having separate instruction and data memory. So far I've been drawing these as separate, but what if we had only a single memory that we use for both? In this case, it would only be a problem when you had a load or a store instruction in its memory stage wanting to access memory at the same time that another instruction is trying to do instruction fetch, right? If that happened, then you'd have to stall the instruction fetch. You would have to wait for the older instruction to load or store to finish using the memory, and you just have to wait a cycle, and we'd insert a stall or a bubble. And we'll look at that in this example here. So here's a load going down the pipeline, and here's another instruction here that wants to do instruction fetch. And imagine instead of having separate caches, these came from the same memory. Right, so this would be a structural hazard. 2 instructions in the pipeline want to use the same thing at the same time. So you can't do that, so what you're going to have to do is, the second example is the register. This was another question somebody had. What if you want to write and read the registers at the same time? If you could only write or read, then this would also be a structural hazard, trying to write registers at the same time. So to solve these hazards, these are the easiest ones to solve because basically all you have to do is throw more hardware at the problem. If 2 instructions are fighting over some hardware, just add some more hardware so they can get their own individual units. So for the register file, we do that in time, and in our designs, we're going to assume that you write in the first half of the clock cycle and you read in the second half of the clock cycle. The register file access is relatively fast, so we can do this. We can actually squeeze in 2 sets of accesses within 1 clock cycle. So write in the first half, read in the second half. Another thing we could do instead is for that register file, provide independent hardware access paths to the registers. So you can physically, at the same time, read from some registers while you're writing to different registers. Actually provide extra circuit paths in and out of the register file. It's a different way of providing it. And so actually, all machines today, it's very common. You can read and write multiple registers in the same clock cycle. And for the memory system, we've already seen the solution, which is provide separate instruction cache and data cache, so you don't get a conflict between those parts of the instruction execution. Sorry. So, basic thing to remember, structural hazards are all about hardware. And you can always remove the hazard by adding more hardware. Okay. Excuse me. Data hazards. So with data hazards, let's consider this set of instructions, right? We have an add producing a value in register T0. Then we have a bunch of instructions that will read that value in T0. Excuse me. So, getting back to this diagram, as somebody pointed out earlier, here's the add instruction that's going to write to T0. So it goes down the pipeline, and this is where the write happens to the register file. This instruction, we started a cycle later, it wants to read the register file here. So, barring inventing a time machine, there's no way for this guy to get the value this guy is going to write over here, right? How is it going to get this value at this point in time? Similarly, this guy is also trying to read, even at this point, is still earlier. Now, at this point, if we write in the first half and read in the second half, the value will be available in here and also for this instruction. So these two instructions have a problem. They're trying to read a value that hasn't been written yet. So this data hazard is an example where you have a difference from a car assembly line. A car assembly line, all the cars are independent. You don't care about one. You can sort of take one out. It doesn't matter. But remember, when you write assembly code, the programmer, the semantics of the program depend on everything that's happened before. So I expect that all previous instructions are finished before I execute my next instruction, right? And what we're kind of cheating here, we're trying to get all these instructions overlapped and execute them in parallel. But we have to preserve this illusion to the programmer that everything happened one after the other, right? It's not acceptable to just give your hardware to return the old value of T0 in this case, right? That would just be wrong. You would really freak out the programmer, like, what happened to my new value of T0? So you're not allowed to do that. You have to meet the specification of the processor design. So this is showing the red arrows are the ones that are illegal, right? You cannot do this because you're going backwards in time. These ones are okay because the value is written before you try and read it. So one really cool trick you can do is called register forwarding, or sometimes register bypassing. And the trick here is, I haven't written it to the register file yet, but I do know the value I'm going to write to the register file when I get there, and it's sitting inside the machine at a point that I can steal it and sneak it into the next instruction. So notice in this add, I do the instruction fetch, the decode. Here's my ALU operation. So actually at this point in time, I already know the value that's going to be written to T0. I've completed the add, and the value is sitting right here. Okay? And notice this guy wants to read it here, but why is it reading it here? It's because he wants to work on it here. So I can just take the value from this point and feed it into this guy. So I add this extra sneak path of, I already computed it. I haven't written it back, but I know what it's going to be. And if I detect that situation, I'm just going to forward the value from the output of the ALU back to the input of the ALU. So this now means I can do back-to-back dependent instructions, one cycle after another, at full speed, right? Even though the whole instruction takes 5 cycles to get through the pipeline, this critical piece I can do back-to-back, right? And similarly, for this instruction, it's even easier. This just needs the value here. I know the value at this point, so I can forward it from here to this input, to this ALU. These guys doesn't matter. And these are the forwarding paths I'm going to add to the hardware design, right? So the key here is that I know the value, I've already computed it. It exists in the machine at that point in time. I just need to route it by adding some extra circuitry to get from where it's produced to where it's needed, right? So by doing this forwarding trick, you could actually get you can execute these instructions in one of the pipeline clock cycles, even though they depend on each other. Right, question?
So in this case, it's specific as to, we know which ones require which values, but how would you do it in a general sense? So how would you implement the following?
So the question is, in this case, it's for specific values?
It's specific as in we know which instructions require which value, but just in a general sense, how would we sneak that?
So, okay, so the question is, in this specific case, you can sort of see which values are needed and you can figure it out. How do you do it in the general case? Well, the general case is actually pretty straightforward. For any instruction, you decode it and find out, does this instruction write a register, right? If it writes a register, where does it generate the value that it's going to write to the register, right? So all the ALU instructions all produce the value here. They do write a register and it's ready here. The second step is all instructions that read a register, what register are they reading? You just need to check for any instruction in the pipeline ahead of you, is it writing a register that you want to read? Right, that's the general thing. Are you writing a register that I want to read? If so, have you produced a value? If so, can I just forward the value on instead of waiting for you to write the register file? Question? Right, so we'll do load word next. So good call. That if you notice for loads, the value is not going to be ready until here, right? So you have to, you still cannot go back in time. We haven't invented a time machine here. All we've done is notice that the value we need is already being produced at some point in the machine. And we're just going to sneak over and grab that value that's already produced. However, if the value is not available in the machine, there's nothing we can do. So let's first look at what we need to do to implement forwarding for this case. How do we change the data path? And so this is the basic data path we're going into ALU here. And we're just muxing whether we have an immediate or the register value going to the ALU. What we're now going to add is a forwarding unit that checks the source registers, RS and RT, the registers that I'm reading, compares them against earlier instructions, what registers are they writing, so is there a dependence? Am I depending on an earlier instruction? That's the first thing. Compare RS and RT here with the destination register of the later instructions, right? Remember that we captured the instruction register and shifted it down the pipeline, and one of the things we captured is which register am I going to write, so then when I got to the end of the pipeline, I would write the correct register. So that information tells you which register is going to be updated by that instruction. You compare that with your source operands, the registers you're going to read. If there's a match, you know that, oh, I need that value that's still in the pipeline, right? So you're comparing all these register numbers here with my source register numbers here. If there's a match, I set these muxes here to forward the data value back to the input of the ALU. So this is where I'm sneaking this value and feeding it back around. Notice I've already read the register, but that's the old stale value, and I just ignore that value. I read it anyway because I don't know any better at that point in time. I read the old value in case I need it. At the same time, I check if there's a newer value in the pipeline for that same register, and if there is, I mux that one in instead of the old value I read from the register file. So that's what these muxes are doing is one path comes from the old value in the register file, but if there's a match, I read the new value and mux that in instead. So then I get the new updated value and get the correct value to operate on. So notice I've had to add, quite a substantial amount of hardware and some new signal paths. This hardware that does the checking for those data hazards and determines whether you can bypass. Plus, I had to add the muxes. So this is control logic. Plus, I added these muxes in the data path to give me a way of connecting these signals back around. And notice I can mux on either side. It can be either the RS or RT side. I can read operands on either one of those places. So I need muxes for both RS and RT to do all the forwarding. So this is the problematic case somebody brought up about loads. So what about loads? Now, forwarding worked because the value was in the machine and available at that point in time. Now, with loads, you have a problem that it's not until I get to the output of the memory that I have the value. So this load instruction, if I then follow it with a subtract, this is just the address of the memory. So I can't use that. And I can't go back in time from here into here. So I cannot forward the load result, right? I just have to actually wait until it's really present in the machine, right? So forwarding won't always work. You can't solve all the data hazards with forwarding, only when that value is actually available somewhere in the circuitry for you to forward from it, right? So in the case of a load, you just have to wait until the load resolves. So if you cannot forward and you have a data hazard, what you're going to have to do is stall those instructions until the older instructions are finished and produce the values you need, right? You're going to have to stall the new instructions. So this is called, adding these stalls is called interlocking. I'm just, I see a data dependence. I'm dependent on that old value. It's not ready yet. I have to wait in the decode stage until the old guys have produced the values I need. So kind of what this looks like, it's like this. So load instruction goes down the pipeline. At this point, it produces the value. So this instruction starts off, but then I realize, wait a minute, I need this value, but it's not ready yet. So I'm just going to have to wait around and do nothing, like basically repeat this again until now I can pass the value into the ALU. So this introduces what we call a bubble in the pipeline. A bubble is just something that goes down the pipeline with no work inside it. It's like a no-op, right? Nothing happens in those pipe stages. And what's happening is you're just spacing apart the instructions to make sure the hazards are okay, to remove the hazard. So if I cannot tightly pipeline them, I'll just insert some space so then I can correctly pass the values between the instructions. Right, so then this is showing the actual bypassing path from the output of the memory to the input of the ALU. Right? So now one issue here is how does this stall actually happen? Well, it kind of this is what you draw sometimes, but the way it really happens is animation's broken here. All right. I think I've got some broken dependencies here, something. Yeah, out of order. So here's a load coming in, right? This is when the value is produced. So this subtract comes in. I try and fetch it, decode it, then I detect, oh, whoops, I've got a hazard. So what I do is I kill this thing and turn it into bubbles. So the bubbles then flow down the pipeline. This guy actually stalls and repeats the same stage, right? So this was in the decode stage. I make it repeat the decode stage. So this guy stays in decode stage but sends a bubble down the execute stage. And the bubble is just like a no-op. Nothing happens. It's just empty stuff in these stages. So this guy just repeats this stage. But also, there's kind of a backup because this guy is stuck in decode. There's another instruction, an instruction fetch that's already happened. And that has to wait as well. So everything behind the instruction that's blocked has to also stall. And it's sitting here. So this guy repeats the decode stage. This guy repeats the instruction fetch stage. And then we just insert these bubbles and they flow down the pipeline. So the hardware dynamically adds this in. And so it kind of just slips the pipeline apart, inserting that space to satisfy the data dependencies, right? So this is called hardware interlocks. So the one thing you're thinking about, this is interesting. You have this, what we call a slot. After a load, you cannot use the value for one cycle, right? So the hardware, if you try and do that, inserts a no-op, a bubble. You could actually have done this without the hardware doing this by requiring that the software programmer, you could have written a specification saying it's illegal to use the value of a load in the next instruction, right? So you could just tell us, hardware guys, they have a hard life. Hardware's hard, right? Software's easy. So you kind of shift the pain to the software folks and say, look, this is hard to take care of, so just don't do that in software, right? Just do not try and use a value one cycle after the load. And this is actually what MIPS did in the first version of MIPS. They actually had that as part of the specification of the machine. So at the assembly code level, you were not allowed to use a load value in the next instruction. If you tried, what you should do if you wanted to is place a no-op, an explicit no-op instruction to explicitly space them apart and then do the use one cycle later. Right? So MIPS actually stands for microprocessor without interlocked pipe stages. That's what the acronym means. And they were trying to minimize the amount of control logic And this is one of the ways they did that. They got rid of the interlock and instead made the software guys take care of it, right? So that was version 1 of MIPS. Version 2, they added the interlocks back in. And the reason was that those no-ops take up space in the program, and they take up space in the cache, and they actually hurt performance more than they help. So they sort of fixed it later. But for the first version, the programmers had to not use it in the next cycle. Now, a better idea here is that, provide the hardware interlock, but the compiler knows that this hazard exists. And so what it can do, when it's compiling code, instead of you manually writing code and putting no-ops in, if the compiler has a choice, it can change around the order of the instructions, if it has some freedom, and try and find a different instruction to place in that space that does some useful work, not just a no-op, and avoids the penalty. So here's a little example. Let's calculate D equals A plus B equals A plus C. There's a little bit of code that does this in MIPS. So load, this is doing this expression, load, add, store. And then for here, load C, add, and store. And here you see there's between this load into T2 and this use of T2, there'll be a load delay slot here. There'll be a penalty here. And similarly here, between this load of T4 and this use of T4, there'll be a penalty here, there'll be a hazard and a bubble. What you can do is have exactly the same result, but much faster. So this takes 13 cycles. If you just remove this code, this load, you can move this earlier, right? So I'm just rescheduling the instructions, writing them down in different order. It has exactly the same effect as the previous program, but now I spaced apart this load of T2 from this use of T2 and put this independent instruction in here, right? And similarly now this load of T4 is separated from the use of T4. So now this runs in only 11 cycles, right? So by being aware of the pipelining and the hazards, I can shift the code around a little and make it run faster, right? And so this is what modern compilers do all the time. They understand, both these programs are semantically the same. They mean the same thing. But by reordering the instructions, one of them goes faster than the other, taking advantage of what you know about the hardware underneath and how it will execute. Okay, so quick in the news. So, before that, question? I think this included the startup and the pipeline ramp up and wind down. So as you fill the pipeline up, and then you drain the pipeline at the end. I think that was added on. Right, but basically, I think the most important is the difference. 13 minus 11 is 2, and those are the 2 store cycles that you save. That's the real number you should think about, is the difference between the 2. Okay, so in the news, so you think you had a big flash drive in your laptop. SanDisk just announced a 0.5 petabyte flash drive. 0.5 petabyte, right? That's 512 terabytes of flash in a disk, right? Now, this is a pretty big disk. It's a 3U rack thing. It's about this big, so it won't fit in your laptop. But this is much, much, much denser than even disk drives in that amount of space, like 512 terabytes of solid-state memory in a 3U rack space. And it can sustain 7 gigabytes a second of bandwidth out of this array. So this is like an enterprise class disk array for data centers, right? So your Facebook feeds will be living in this kind of stuff sometime soon. But one thing to think about, that's 2 to the 49 bytes of storage just in 3U of a rack space. So pretty soon we're going to run out of, you thought 64-bit address space was big, but we're kind of running out of 64 bits of address space sometime in your career in the next decade, right? So 512 terabytes in 3. I don't know how much it costs. I think if you have to ask, you can't afford it. So nearly 1 million IOs per second out of this thing. So quite incredible. But yeah, so this is solid-state memory. The flash is denser than disk drives. Right. Okay. All right. A little bit of time. Let's take a 2-minute break. The next part is really hard, so let's take a 2-minute break. Okay, let's start up again. So probably a few years, but then you'll all have 512 terabyte laptops, probably. Control hazards. So we left this one to last because this is the worst. So the problem here is I have two instructions going down the pipeline. The first one tells me which instruction I should do next, right? So I want to do a branch. You know, I don't know where to fetch from until I've resolved the branch. And so in the MIPS we have, the simple MIPS, we looked at branch equal, branch not equal, instructions, conditional branches. Now one simple solution that's correct, and it's always good to think of correct, simple solutions, is just wait. So what you can do is when you see a branch instruction come down the pipeline, just don't try and move ahead down the pipeline. Just wait until the branch resolves, and only when it resolves, go fetch the correct target instructions. That's a reasonable, correct thing to do. The problem is, in our pipeline, that would add 2 cycles, 2 bubbles to every single branch. And branches are like a fifth or a sixth of all instructions executed at branches. So this would be kind of terrible for performance. Like if every branch took, an extra couple cycles, this would really hurt your performance. Question? So suggestion is, when you come to a fork in the road, take it. Go both ways, right? Let me come back to that when I talk about speculation. All right, let's assume you have a simple machine. We can only go one way. But I'll come back to that later. That's a good point. So here's what's happening. Have a branch instruction, go through fetch, register read. Now we make the determination, right? So we compare our current design, we compare the branch here in the ALU stage. And so really it's only at this point that we can correctly fetch the next instruction, right? So these 2 cycles are kind of wasted. That would be the extra 2 bubbles we'd have if we were very conservative on the branch. One thing we can do is try and do that branch compare earlier. And this is one reason why the MIPS branches only have these 2 kinds, equal or not equal between 2 registers. It turns out you can do a quality compare a bit faster than doing magnitude compare. So they don't have a branch if less than or a branch if greater than. They only have a branch if equal or not equal. And one reason they did that is they could fit the branch comparator into the end of the decode stage. And this reduces the penalty. So instead of determining here the branch condition, they would add a special circuit that would do it as soon as the values were available at the start of this cycle. And so by doing that, you chop the penalty down to only 1 cycle now. So you've halved the penalty now by adding this extra circuitry. So notice this is a case where the instruction set design has been influenced by sort of circuit and pipelining details, right? And in fact, the whole RISC instruction set is designed around allowing you to build efficient pipelines. It's not about having as few instructions as possible. It's about building machines that are fast, that are good at being pipelined. That's where the RISC ideas really come from. So this is another example of thinking about the implementation in designing the instruction set. Right, so they could cut the branch penalty down to 1 cycle this way. Now, a very common way that people actually handle these ways is when you get a branch, guess. Right, guess which way it's going to go in the hardware. Make a prediction. Right, so you don't know exactly the value of what it's going to be, but just guess what it is. It's probably the same as it was last time. And then just run down that pathway, and if you're wrong, you have to flush all the pipeline out, kill all the instructions in the pipeline, and restart over at the right place. So this is speculation in a pipeline. Now, it turns out there's a very, very simple form of speculation we can do in our simple pipeline, which is almost what happens anyway if you don't think about it. You always add PC plus 4. So if you just keep doing that and don't worry about whether there's a branch or not, in effect what you're doing is predicting the branch won't be taken. You're predicting that it'll just fall through and you'll keep running sequentially. So the simple thing you can do is just keep fetching PC plus 4. When the branch resolves, if the branch was not taken, you've done the right thing. There's nothing you need to do at that point. Just keep going, right? That was fine. You did the right thing. It's only if the branch was actually taken, you have to kill the instructions that you fetch sequentially after the branch, right? That's the only case you have to repair. So this is a good thing. Now, this predict not taken is what you would do with our simple pipeline. These days, modern machines have extremely sophisticated branch predictors. They spend, many kilobytes of memory updating tables that predict the way branches go. And they will do things like they can detect if you're going to call a subroutine and if you're going to return from a subroutine, where you're going to go to. They can predict how many times you're going to go around the loop counts. Now, a lot of hardware is put into branch prediction because it's one of the worst hazards in modern machines. They spend a lot of effort fixing it. For our simple pipelines, though, for our simple pipeline, this one would work pretty well. Now, get question?
Yeah, so what would you do if you chose the wrong branch, right? So you just chose P13 plus 4. You might be modifying a lot of values there, right? How do you, when you figure out that it was wrong, what would you do to fix it?
That's a great question, actually. So let me go back to this diagram. So the question was, what if you just, let's take this example. I do a branch here, and I just keep fetching sequentially. But then here I determine, whoops, that branch was taken, so this instruction was wrong, right? I fetched sequentially, I should have gone to the target. So the question was, what if this guy messed up the machine? How do I undo that? Because I went down the wrong way. Well, the other nice thing about the way this pipeline was designed and the instruction set was designed, I don't actually update any state till I get to the end. Or at least I get to the memory stage. So provided I can find out before these guys write to memory or the register file, I can just blow them away and nothing will have happened. So we design the instruction set so all the updates happen at the end of the pipeline. And so there's kind of no permanent change made until you get there. Now what might happen is this guy produces a value and I forward it to some other instruction. But notice when I forward the values, I still haven't written it to the register file. That's just kind of an early, sneak look at the value when it will get there. And so I haven't changed the value in the register file. So it's okay to blow things away until they get, the hard part is if you actually did write to the register file or wrote to the memory. They don't have to worry about undoing it. But we designed the pipeline so that won't happen. Great question. Okay, so the prediction. Now, like I said, hardware guys always like to, pass the buck up to the software folks because they have it easy, really. So make the hardware guys easy. Another thing you could do is just redefine what a branch is, right? So what you're going to say now is the regular definition was when you hit a branch instruction, evaluate the condition, and either go to the target or keep going sequentially. Let's change the definition. What we're going to say is when you get to the branch instruction, we're going to evaluate the condition. We're going to keep going for a little bit, and then when we're ready, we're going to jump. So after the branch, we're going to execute the next instruction, regardless of which way the branch is going to go. This is called a delayed branch, or a branch delay slot. So when you see a branch, the next instruction is always executed, and then the branch is taken. Okay, so this seems a bit crazy, but I'll show you a non-delay branch, what you would expect if you're a software person to happen. If I see code like this, or and subtract branch of equal XOR, the branch is taken, at this point I jump to exit, right? That's what you'd expect to happen. But in a machine with delayed branches, what actually happens is see, I'll move this OR instruction down here. After the branch, the next instruction is always executed, and then the branch is taken. So now if you think back to the pipeline diagram, you understand why you do this. It means you never have to kill. You don't have to do anything about control hazards in the pipeline. Right? I'm just going to, oops. I thought there was a slide on this. Let me go back to this slide. The idea is this instruction is the branch. The following instruction is always executed. And at this point, I'm ready to tell me the right answer. So it's always correct for the machine to execute one instruction after the branch. I never have to kill the instruction. I don't have to predict anything. I just always do the next instruction. Right? So you just change the instruction set semantics. So branches now do this. Branches have a delay slot. And so what the software has to do, the compiler or the assembly level programmer, they have to make this transformation of finding. So what they could always do, if you didn't know anything else, you could always put a no-op in here. So I'd explicitly code a no-op if I didn't know what was going to happen after the branch. And that no-op would always be executed. However, you can usually find some independent instruction ahead of the branch that you can move down and fill that branch to delay slot, which is what happened here. This OR instruction, it writes register 8. The branch doesn't depend on this instruction in any way. Right, this 8's not used by these instructions. So this OR instruction, I can just move it down and put it in the branch delay slot. So now the branch happens a cycle earlier. This happens in the delay slot. And I'm at exit. And I don't have a control hazard anymore. It just magically disappeared. There's no hardware. The hardware is very simple because it's not doing anything. I just redefined the software interface to make the hardware life easy, right? So this is actually what's in MIPS. So MIPS has this delayed branch. And in fact, this is one of a lot of the early RISC machines had this delayed branch instruction in. Yeah, so the worst case is you put a no-op in there. If you can't find anything better to do, just write a no-op. The better case is you actually find some useful instruction that you can put in there. And, statistics for a simple pipeline like this, usually, I'd say it's actually a bit more than 50%. It's more like 70% of the time you can find a useful instruction to put in there. The other 30% of the time you put a no-op in there. And it's not just branches, you also do this for jump instructions. So any control transfer instruction in MIPS has this branch delay slot. So they don't actually take effect until one cycle later. Okay, so this is just a sort of introduction to pipelining, 61C. And this is, I got a question at the break. This kind of material was sort of really developed in the late 40s, early 50s, this kind of pipelining. And architects have been busy ever since. And so some of the things you'll read about are going to even deeper pipelining. So we just looked at 5 stages. Some processes went up to like 30 or 40, well, 30, mid-30 pipeline stages to execute one instruction. And somewhere in the middle of that will be the integer add, taking one clock cycle out of 30-something. Also, instead of doing one instruction at a time, you can actually do 4 or 5 or 6 or 7 or more instructions at the same time in one clock cycle. And, dependencies are a problem, so what you do is execute instructions in different orders. So on the fly, you reorder the instructions to remove dependencies so you can run faster. So it's called out-of-order execution. You don't execute instructions in the order they were given. In hardware, you reorder them on the fly to get greater throughput. So all this stuff is real fun. If you want to find out about it, you should take 152, where we cover these techniques in more detail. For now, we'll just stick to the simple pipeline you have. That's enough to cover the main idea. So just to summarize, this is all about pipelining. This is one of the great ideas, parallelism. You get greater throughput by overlapping different stages of instruction execution. You want to balance the pipeline stages to get the highest clock rate. And there's these 3 types of hazards, structural, data, and control, that limit performance. Structural is just about sharing hardware. So adding hardware always fixes a structural hazard. Data is when one instruction produces a value another one needs. And we looked at forwarding is a good way of removing the data hazards when you can. And if you cannot do that, then you can just interlock and wait for the value to be ready. Then finally, control hazards, where you have control flow and you don't know where the next instruction is coming from. Then you can do these various branch techniques. Okay, that's it. See you on Tuesday.